Welcome to the Public AI Cafe. Today we present our speaker, Vincent Andrearczyk. He is a PhD, has a PhD and is associate researcher at the Institute of Informatics at HES-SO Valais. With his talk, Generalizability, Interpretability, and Interaction with Clinicians, some essential ingredients for developing medical imaging models. So I'm Carmen McWilliams, welcome. I'm the moderator. I'm from Grassroots Arts, a company in Germany, and I'm partner in the European research project AI for Media, which actually funds this cafe. And what is this cafe about? We offer a series of live web sessions. It's an online forum to gain insight into the European AI scene, and participants get the chance to share knowledge and experiences and meet stakeholders from various areas of AI research and application. I welcome everybody who joins today, and please take notice that the session will be recorded. No confidential information shall be shared in this cafe session. In this cafe, the speakers express their personal view and opinions. This is not necessarily the official AI for Media project opinion. So again, this is an interactive session. So if you feel like you have questions, please send them to us over the text chat. You see it on the right side, there's a menu. Just send us your questions and we will read them afterwards and try to answer them. So, to our speaker, here a short CV. Vincent Andrearczyk, PhD, is associate researcher at the Institute of Informatics, HES-SO Valais. His research explores new synergies between technology and societal needs, particularly in artificial intelligence and machine learning applied to medical imaging. The goal of his work is to address complex medical challenges such as detecting cancer or other diseases in medical images and assisting clinicians in treatment planning and patient follow-up. Invariance to image transformations, integration of multimodal data, data harmonization, and model interpretability are of particular interest in his research. So this sounds all really exciting. So I'm very happy you're here. So thank you. You came to us, Vincent. Now it's your time.
Thank you very much for the introduction. So yeah, Vincent Andrearczyk, already introduced, I don't do it again. So I research on AI for medical imaging, and today I want to talk particularly of some aspects that are generalizability, interpretability, and interaction with clinicians that I think are some essential ingredients for developing models in medical imaging. So I will start with introduction of medical imaging. So it is a revolutionary field that allows healthcare professionals to visualize the interior of the human body. Since the discovery of X-rays in 1895, there have been a lot of developments and new technologies. For example, here I have some type of medical images. We have a CT image of the lung on the left. So that is really a 3D version of X-rays. It's used to visualize various tissues and organs, including some tumors, some fractures or blood clots, etc. On the second image, we have an MRI of the head. So MRIs use magnetic fields and radio waves to take 3D pictures of the body's interior. It's more expensive and takes longer than CT images, but it is used to investigate conditions that cannot be detected by CT, such as brain tumors. Then we also have an ultrasound in the third image. So it uses echo of sound waves, and it can be used to study, for example, developing fetus or blood vessels. And also we have another example of PET-CT images. So that's a multimodal image on the left, on the left with a white background. We have a PET image in the middle, a CT image, and then on the right, the overlay of the two. So combining these as multimodal images is used for the complementarity of different modalities. So here the CT image can assess the tissue morphology, and the PET image can assess the metabolic response of tumors. So for example, we use radioactive traces injected in the blood, and they show the glucose consumption, for example, of malignant tumors. So that's where the image is highlighted in red. So all these images provide valuable insights into the structure and function of organs, tissues, and bones. They enable non-invasive exploration, diagnosis, and monitoring of various medical conditions. And in general, the importance of these images lie in early detection, accurate diagnosis, and treatment planning. So now AI can help to analyze these images. So some challenges of medical imaging include the increasing volume of images, the demand for faster and more accurate diagnosis, and the limited availability of skilled radiologists. And the tasks that can be addressed by AI include image enhancement and reconstruction, automated detection and diagnosis, personalized treatment planning, and quantitative analysis, so providing objective metrics for disease progression and treatment effectiveness. So really, it's the collaboration between AI and healthcare professionals that aim to augment the capabilities of clinicians to improve diagnostic, treatment response, and ultimately enhance patient care. So the goal of AI is not to replace radiologists or clinicians, but to help them. Now, what is AI briefly? So that's a simplified vision of AI. There are many other subcomponents and complexities, but so we can define AI as machines that imitate human intellect behavior. For example, a simple AI model could be a rule-based model with if statements, etc. Within AI, we have machine learning that aims to automatically learn from data. So instead of handcrafted rules, we have models that are optimized to fit some data and generalize to new data. And again, within machine learning, we have deep learning that mimic human brain using deep neural networks. I say mimic because it uses artificial neurons, that's all. So that's a type of machine learning algorithm that started recently when we had enough computational power to train deep artificial neural networks. So some examples are convolutional neural networks, transformers, generative models like diffusion models, etc. Now, machine vision, these are programs that identify and understand objects and people in images and videos. So, for example, if we take a simple rule-based model and consider the task of defect inspection on apples, so we can see on the image, we can have an input image of an apple. We can do different steps with blob extraction, feature extraction, and then we manually define rules to construct a recognition, see whether there's a defect or not on an apple. And for example, features here can be the number of blobs, the size, the histogram of pixel values, etc. So here there's no training. We use our knowledge to define the rules. Now, if we go to similar idea with machine learning, we would still extract handcrafted features, but we would train a classifier to predict the outcome, so the classification. For example, we could have a support vector machine, and here we would really use training images to fit the model. And if we consider a deep learning model, so we could here have a convolutional neural networks that learns feature engineering and classification all by itself. So we would remove the feature extraction and the manual rules, all replaced by a neural network. So here we'll talk generally about AI, but we'll mostly be interested in machine learning and deep learning models that learn from the data. Now back to medical imaging. So there are similarities between natural and medical images. So they have pixel intensities, there are some shapes, some textures, but what distinguishes medical images from natural images? For example, we often have limited data, so it's easier to acquire images of cats than of patients. Sometimes we have a rare disease that would cause a high class imbalance for the training. We often have 3D images, multimodal images instead of standard RGB pictures. There's the cost of annotations by experts. Also, there's sometimes a ground truth uncertainty when experts disagree. There can be noise and artifacts because of the imaging equipment, patient movement, etc. We need also to consider data protection with the consent patients, anonymization, ethics approval, data transfer agreements, and sometimes federated learning when data cannot exit hospital, but we would still want to train models on data from different hospitals. Also, the impact of algorithms on people's life, and sometimes some specific tasks such as survival analysis. So building AI models for medical imaging really requires specific care to take these particularities into account. So now I'm with these three ingredients that I think are important. I will define them. So starting with generalizability, so that is the ability of an algorithm to perform consistently across diverse data sets. When we train a model on some training data, we want it to perform well also on new unseen data when we deploy it. Important concepts here are quality of data, the quantity of data, overfitting that we want to avoid, that is represented below in the image, multicentric data, domain shift, and harmonization. So this symbol here, I will use it throughout the presentation, that represents a domain shift. So there are two Gaussians that represent the shift between two data distributions. So that can be some training set from one hospital and a test set from another. So we want to be robust to this domain shift. Now, interpretability, that is the translation of the working principles and outcomes of the model in human understandable terms. We often refer to it as opening the black box. That's why I'm using this symbol again here. And on the figure below, we have examples of human understandable terms and how we perceive them. So a bird has wings, has feathers, it can fly, so that's a bird. Now, interpretability is important for different reasons. So it can be for user understanding, so the users, the clinicians in our case, error diagnosis and improvement, so for the developers, safety and reliability, trust and adoption, ethical considerations like identification of biases, ensuring that the AI systems are fair, and also regulatory compliance, so because we have requirements for transparency and accountability. And now the last ingredients, the interaction with clinicians, I think also very important here. The symbol is quite self-explanatory. It's just a clinician. And so why is that important for defining clinical objectives, for data annotation and ground truth, for ensuring that AI models reflect the complexity of real-world clinical scenarios, and for validation and evaluation of models. As a side note, also, we can have different background and knowledge between computer scientists and medical doctors, and also different terminologies. For example, we had this work to harmonize terminology in explainable AI. So these are really challenges that need to be taken into account. So the communication. So these are again our three ingredients. They are somehow linked. So, for example, interpretability can be used to explain model behavior to clinicians or to ensure robustness or generalizability of the models. I will now present some of our work, and maybe you will find these ingredients in these works, or if not, I will point to them anyway. So these are the different research projects that we'll present now. I will start with AI for brain lesion management. So that's a work done in collaboration with the Lausanne University Hospital, led by Professor Andrearczyk here on the left, on the left, and also other collaborator at CHIV. So brain metastases originate from cancer cells that spread to the brain from other sites or other primary cancers. And the cancer cells pass through the bloodstream, enter the central nervous system through a breakdown of the blood-brain barrier, and then proliferate in the brain. It is the most common type of brain tumor and a major cause of morbidity and mortality. MRI is commonly used for diagnosis and follow-up. We have an example of MRI on the top right. And treatments can be medication, surgery, whole brain radiation therapy, and stereotactic radiosurgery. That is what we're most interested in. So it is stereotactic radiosurgery is not a surgery in the traditional sense. We apply radiation beams focused precisely on the lesion, and it avoids irradiating other parts of the brain with collateral effects. And also, when we have multiple lesions, we can treat them individually, and we can also retreat later if necessary. So how can AI help brain metastasis management? We'll start with the automatic detection and segmentation in MRI. So that's the typical workflow. We have a patient that comes that with a suspected brain metastasis. It has an MRI is done, and we want to detect and segment the lesions in the image to then plan the treatment. And after treatment, we have a follow-up every 2 months, and we want to assess the evolution of the lesions and maybe the appearance of new ones. So we want to resegment the lesions and also segment new lesions if they appear. Maybe they can be treated again if needed. So for that, we trained a deep learning model to detect and segment brain metastasis. So we have different models for the detection of new lesions or the resegmentation with prior knowledge of where the lesion was before. We have also single component or multi-components with nodule, edema, and necrosis. So in this image on the right, so the leftmost column is a slice of 3D in MRI, so that's our input. Then next to it, we have the manual annotation and then model prediction for single component. And then on the right, we have the manual annotation and model prediction for multiple components. So it works really well. I don't put all the results, but it works really well despite the wide variety of lesions, their size, the components, and the location in the brain. So if you didn't see it, here we have a first ingredient, the interaction with clinicians. So they are needed for collecting the data, deciding which regions are relevant, annotating the lesions, evaluating the results. So that's really constant interaction. But also the generalizability. Models need to generalize to different scanners, different types of lesions, whether they include necrosis, edema or not, different locations in the brain, different sizes, so, and different patients, obviously. So they really need the generalizability. Okay, now after detection and segmentation, we want automatic lesion nomenclature using Brain Atlas. So that's not the most challenging and innovative technology, but very important for radiologists. We don't want to only detect lesions, we also want to a consistent nomenclature across lesions and across patients. So where they are, in which lobe, where on the x-axis, on the z-axis, for example, when they appeared, etc. So for that, we use affine registration with an Atlas MRI. So on the right, we have the Atlas MRI. So we will come with our the MRI of our patient, and we will align it with this Atlas MRI. And then we use the Atlas regions to locate the lesions. And then we order the lesions from top to bottom, left to right, temporally, etc. And that gives us a consistent nomenclature. That's pretty simple. Now, we want also lesion tracking across time and the response assessment of the treatment. So again, as I said, we have a follow-up every 2 months. So for example, we have these 2 lesions. We want to track them across time. For that, what we do is first registration again. We align all the images so that then we can use lesions overlap and distance of centroids to track the lesions across time. It's not an easy task. There are some lesions that can disappear, some that may be close to each other. The registration may fail. It seems simple, but it's not. And then when we track them, we also want to assess the response. So did the treatment work or not for each lesion? So we want to do it at the lesion level instead of patient level, because remember, with the radiosurgery, we can really target individual lesions. So the different responses are complete response, partial response, stable disease, and progressive disease that depend on the evolution of the size in general. And so we want also to base the response on the volume instead of on manually calculated diameters, because it's more stable. And that we can use the volume thanks to the automatic segmentation, because traditionally the longest diameter on an axial plane is calculated manually and at every time point. So now we would also like the prediction of lesion evolution and patient outcome. That's more challenging. So for example, using the initial image to predict the evolution of the lesion if treated with a given radiotherapy dose, or using the initial image and the first follow-up to predict the evolution, the future evolution of the lesion. I will skip the details here, but that's work in progress. So I will move on. But again, we would see if, that there's the need for interaction with clinicians and for generalizability, but I will skip that for now. So these were the tasks that we addressed with the machine learning models, but what about interpreting the models, opening the black box? So this is a work done mostly by Federico Spagnolo on the left picture. We have a deep learning model trained to segment lesions. So here we have two input modalities on the left. Then we have a model that is a unit model for segmentation. Then we have the final segmentation on the right with the final predictions on the right in red. And so we would like to know where the model looks to say that these are lesions. So there are methods like GradCam that use gradients of prediction to create a heat map, M on the bottom left here, that shows which region in the input is used by the model for prediction. But when we have multiple lesions like this, we would like to have explanations for individual lesions. And that's what Federico did. He developed a method to select a single lesion and provide a heat map that shows where the model looks at to predict this one as a lesion. He did the same also for other methods that were originally developed for classification tasks and not segmentation. So I will skip the detail, but just go to the conclusions. Here, what we showed, for example, here is that bright voxels inside the lesion and the edges of the lesion are responsible for the detection. And in another experiment, we also showed that the main point was that information is taken very locally for the model to make predictions. So these are just examples of how we can use the interpretability methods that we develop for interpreting our models. So now we move to the second research project, so head and neck cancer. So that's a work led at our institute in collaboration with many partners, clinicians, and AI researchers. That's what many universities and hospitals here mentioned. For head and neck cancer, so in particular, there are more than 130,000 new cases of oropharyngeal cancers reported per year in the world. There's a high mortality rate, and PET-CT are modalities of choice in oncological imaging, including head and neck cancer. Treatment possibilities are surgery, radiation therapy, chemotherapy, targeted therapy, depending on the stage and localization of the cancer. But there is a high local failure with about 40% in the first 2 years following treatment. And for that is personalized medicine is important, so that finding the best treatment is crucial for patient outcome and well-being, individualized treatment. And AI can help, again, assist clinicians for head and neck cancer treatment using PET-CT images. First, with the tumor segmentation again. So there is a high interest for tumor segmentation for treatment planning, for looking at the evolution of tumor volume and aspect across treatment. Also for manual contouring is tedious and error prone. And in the state of the art, there were many attempts from simple SUV thresholding to deep unit ensembles, etc. So we also see the growing interest in publications over the years. But so there is a need for a standard approach to systematically evaluate and compare state-of-the-art algorithms against the same test set and with controlled conditions. That's why we created and led the HES-SO challenge, the head and neck tumor segmentation and outcome prediction challenge for 3 years in a row. So in this work, we gathered data from different hospitals, we cleaned it, organized the annotations, and then we organized a competition at a major medical imaging conference where different AI experts can compare the algorithms on the same data with controlled settings. And that is really important to evaluate the status of state-of-the-art algorithm and their readiness for clinical use. So another aspect is also patient outcome prediction. So the idea is really to find image biomarkers that are predictive of patient outcome. very important to find the best personalized treatment. And we also again see a growing interest in the last years. So in the state of the art, they were targeting different risk groups, so local regional failure, distant metastasis, overall survivals, etc. And C indices were reported in the range of 0.6 to 0.8. The C index is a metric of survival task, so to predict time that passes before an event. So in this case, the event is tumor recurrence after treatment. So again, there's the need for a standard approach to systematically evaluate and compare the state-of-the-art algorithm against the same test set and with controlled conditions. So that's why we conducted the second task of the challenge that we organized, the patient outcome prediction. Again, allowing research teams across the world to compete and to compare their algorithms. So the take-home messages of this challenge were that segmentation of primary tumor and metastatic lymph nodes work really well automatically, and it seems ready for clinical deployment with obviously clinician supervision. And for the outcome prediction task, the best C index were around 0.7. That seems not sufficient for clinical use, but the clinical partners were already really interested in these results. So for information, C index of 0.5 would be a random prediction, and 1 would be perfect prediction. So back to our ingredients here. Why was interaction with clinicians important? For the collected data, we had data from 9 hospitals, more than 1,000 cases, also to define annotation guidelines, to then annotate the data, to define the relevant tasks that we want to implement, and to evaluate the results. And also the generalization. That is, we want models that generalize to new centers, to the variation of scanners, of resolutions, of acquisition and reconstruction parameters. For example, on this figure here on the right, we can see the difference across 2 different scanners. The image look different just because of the variation. On this topic, if interested, we also have work on harmonization at image level and feature level. So if you're interested, you can check this out. Now, another related work is multitask. So we have deep learning model that is trained both for segmentation and outcome prediction. So on the left here, we have a learning model only trained for outcome prediction. And on the right, the multitask model where segmentation is learned in parallel to the outcome prediction. The idea here is that image features that are learned to segment the tumor can be beneficial to predict the patient outcome. And I showed that to go to the interpretability, again, opening the black box. So here we have heat maps that show where the model looks at to make predictions. And 2 things that we can see from these results are models trained with multitask on the top are more focused on the tumor than those that are trained only for outcome prediction on the bottom. And also on the rightmost, we can see that models look both at the primary tumor and metastatic lymph nodes, even though they are trained only for primary tumor segmentation. So that's interesting interpretabilities that we can make. I cannot continue. Okay. So that's it for head and neck cancer. We'll now continue with the third project, that is concept attribution and discovery. And that work was not developed for a specific task like the previous ones. It's more general methods for interpreting and improving machine learning models. This work was done mostly by Mara Graziani on the left. So these are the questions that we ask ourselves for. So starting with what concepts are used by my deep learning model to make a prediction. So how relevant is a given concept to the model output? So for example, if we try to classify, to recognize a zebra, what is the relevance of the striped texture in the classification of the zebra? Or similarly, if you want to classify, to predict retinopathy, that is a disease, what is the relevance of vessel tortuosity in the retina images? And that's where we developed regression concept vectors mostly matter. That's a postdoc explanation method. So we have a model that is trained and we try to explain it. So here we have a simple example with a digit classification, the image on the left. And so that's our input X, then we have the model and the prediction that is f of X. We have some concepts, that is pixel counts, shape, orientation, and we want to know if they are used by the model for classification. What we do is we take internal representation at a given layer in the model, and we do a regression of the concept values for many input images, and we obtain this vector VC. And so first, if we can regress this information, it's probably present in this layer. And then what we do is we compute directional derivative of the output f along this vector, and this tells us how the output is influenced by a given concept. More details can be found in the paper. That was a bit quick, but how we used it. First, we have an example here of deep learning for automatic breast cancer grading from histopathology images. And what we showed here in this work is that nuclei texture emerges as a relevant concept in the detection of tumor tissues. Another example, staging of retinopathy of prematurity, that is a disease that affects premature infants and can lead to blindness if not treated early. And we try to detect that from images of retina. And we have a deep learning model that predict the staging. And what we showed is that curvature, diameter, and tortuosity of the vessels in the eye are relevant to the classification. So now, can we discover concepts automatically in my model? So in the previous slides, we had manually defined concepts to analyze, but can we find them automatically? I decided not to present these for time constraint here, but I recommend to check out the papers. The work was done again by Mara Graziani, Mosley, and Laura O'Mahony. It's very interesting and recently published. But I will move directly to, can I teach my model to use concepts that I know are relevant? So in the previous analysis, we showed that, so if in the previous analysis we showed that some concepts are not used, maybe because there's not enough data to learn these concepts, we want to teach the model to use these concepts. So, or alternatively, to teach it to not use some concepts that we know may be misleading or may hinder generalization. So that's our work on guiding models towards relevant concepts with multitask learning. So here we have an input X, input image, and we classify it with 3 classes. That's our main task. Can be 3 classes, could be other classification. And we also train in parallel to predict the relevant concepts that we define with auxiliary tasks. And we also have adversarial training to forget concepts that we know are misleading with the adversarial task. So we have these 3 tasks in parallel. There can be more, but these 3 tasks in parallel. And here what we applied it on was cancer staging from histopathology images. The auxiliary tasks were nuclei size, shape, and vesicular appearance. We knew it should be useful for the prediction. And we made the model adversarial to the domain, so the hospital where the data was coming from. So we do not want you to use features that are specific to a given hospital and won't generalize to other hospitals. And overall, we showed that this concept guidance with multitask learning improved the performance of the model on the main task, so cancer staging. And I'd be very happy to finish with this example because it's a typical example of the 3 ingredients in our recipe. So we have improved interpretability because we know which concepts are used by the model. We have interaction with clinicians because they need to define which concepts should be relevant. And we also have improved generalization with domain adversarial. So we want a model that will work better on data from a new hospital. So with that, that's it. And I want to thank my colleagues at HES-SO and other partners, particularly the Professor Adrien de Persinge on the top left, that leads many of these projects together with Professor Henning Müller, and also the fundings that made this research possible. Thank you for your attention. If there are any questions, I'm happy to.
Yes, very interesting, and of course, very, very important research you're doing. So I back and I ask the audience, please send us questions. Meanwhile, I start with my questions. So send it via chat. Yes. Do you do clinical trials? I mean, you have all these partners. How you do clinical trials?
So we are not at the level of clinical trials. We do early research on new research questions. We are a bit far from the clinical deployment. So I think clinical trials also mostly for drugs, so in that sense, AI can help drug discovery and all of these. But we are at the level of helping, for example, radiologists with some clinical tasks of, for example, detecting lesions and all of that. I don't think that applies to clinical trials. So. Yeah.
Okay. There comes right away from also our participant. One moment, Tony. Did you evaluate how helpful your methods are for clinicians' work?
So we have ongoing tests with user tests with clinicians. So we evaluate different things. So I don't know which project we are talking on, but in general, we can assess whether they would maybe understand better a model, if we provide interpretability, whether they would trust the model a bit more, then whether they would be faster at some tasks because they have some help from AI, whether they would be more consistent, so there would be more agreement either between different radiologists or even for a single radiologist because he's using additional information coming from AI. So yes, we are doing this type of user tests.
Yes, so back to me. It was actually for the head and neck cancer, you said that you have 0.7 rate. 1 is perfect, 1.5 is random, but you have already 0.7, which is interesting to clinician to use it. No? They're interested at least. No? You said that.
So that's an interesting typical shift from what we expect and what a clinician would expect. So when we saw these results, we were a bit disappointed. 0.7, it's far from a good prediction that we would think of. But clinicians were thinking, that's actually already extracting some valuable information from the data, and sometimes whatever is better than random can be useful. So in that sense, they are already interested. Yeah.
Yes, so it's basically a tool, one of the tools for them to use. I mean, as you are in such a, yeah, I would say difficult area with breast cancer. I mean, how you, I mean, the answer is clear, but how do you make sure that there's no false detection of tumor?
Okay, so the different things for the detection of tumor was not about the C-index. The C-index was about providing a risk score for a given patient to have a recurrence. So that would really give an additional information that maybe this patient could be treated heavier, could have a heavier treatment or lighter one because there is more or less risk of recurrence of the tumor. So that's really an additional information. Then for whether detection can be, there can be false detection or false positive, false negatives. And this, I think, performance of the model is the most important. We want the most performing models. Then interpretability is also important. We want to say maybe why we are predicting this as a tumor, and that can really raise flags that sometimes calculation can be wrong. Also, uncertainty, something that we also work on, is very important. The model can also assess how certain he is about a given prediction. So, yeah, that's definitely to be careful with.
Yeah, I guess the clinicians work in teams, no? I mean, it's the same. I think
yeah, they have two more
because there's
human
failure, there's machine failure, there's software failure, there's everything. But if you work together, I think it's a little bit better.
So many tools that are deployed are also semi-automatic. So they maybe they need the input from the clinician at some point. And anyway, they need the final check. The final decision is made by the clinician.
Yes. So that leads us, of course, to our favorite question always. Do you think your technology is trustworthy AI?
So our work goes towards trustworthy AI, I think. So on the importance of reliability, transparency, robustness, fairness, I think everything I presented, okay, I maybe didn't use these terms, but they are somehow related, and we are trying to go towards trustworthy AI. Yeah.
Yes, thank you. And just, I mean, we know we are far away even from clinical trials, but do you have plans to go with the technology, go to the market, or is this not in your interest at all?
I can speak for myself. That's not really my goal for now, at least. There are many good companies that take care of this. Many also startups that take this from a research project to the market. We are more on early research projects, and that's not the plan
Yes.
But yes. I would like these ideas to reach the market at some point. Yes, but that's just not that different areas. It's not mine.
Yes. So, and now we are coming slowly, 45 minutes over. I'm just asking you something more out of context. So it's our Christmas question, and then we slowly go out. If not, somebody from the audience has a better question, then mine comes, and that question is, globally, do you think AI could help to solve critical, more complex societal challenges in relationship to the UN Sustainable Goals, in this case 3, health and well-being for all people in the world?
That's a good point. So I wouldn't say, I'm not the type to say that technology can solve everything. Definitely not. I think that sometimes can help in some specific areas. I don't think every problem has a solution with technology or with AI, for sure. Then I think AI can be used in a smart way to help in different domains with healthcare, what I showed, but maybe also, I don't know, with education, with environment, maybe with managing resources or modeling the evolution of the climate and things like this. Or with public safety, things like this. So yeah, that would be my answer. It can help, but I wouldn't bet everything on AI. I think we have a decision to make outside of that. Yeah.
Yes. And now to you, how did you come to AI? Are you actually a computer scientist?
I'm originally an engineer in electronics and signal processing, and that's the signal processing that led to image processing, image analysis, machine learning, deep learning. That's how I did my PhD in computer vision. That's where I was first with AI.
And how did you then come to where you are now, to health?
So that was a collaboration during my PhD with the professor that we see here, Adrien de Persinge. I think, I don't know if I'm still sharing the screen, but during my PhD, he was writing a book on texture analysis, so texture in images, and he was mostly interested in textures present in medical images. I started collaborating with him, and then he offered a postdoc in this field, and I was definitely happy to apply what I had learned on medical images to what I had learned for image analysis to medical.
Okay, thank you. So then I am closing down our coffee session today, and I thank you very much
for inviting me.
Yes, it was great to have you here, and it's really nice. I mean, you know that also Mr. Müller, Professor Müller, you're all part in this AI for Media project. That's how we all met.
Yeah, I know, and some of the
Yes.
work that I did was part of the AI for Media with Henning.
So that's why also AI for Media is a good place to meet. And I wish you all a good afternoon. And next year there will be new cafes, but you have to wait for the invitations because we finalized just now our program. So please come back. And I thank you for today. And the recording I will send to you, Vincent. You as a speaker decide if this shall be published or not. Nobody else decides this. So then when you see it, you just basically write to me, yes, no, publish, yes, no.
Okay.
It will be available for everybody if it is published.
Perfect.
Okay.
Thank you very much again.
Yeah, bye-bye.
Bye-bye, thanks.